Our objective today is to learn how to determine a moment about a particular axis. So when we're done with this, you'll know how to determine a moment about an axis using scalar or vector analysis. As usual, there's a lot of extra things in the slides on the course website. Make sure you grab the slides and look through the various quizzes and example problems, group problem solving problems, etc. to learn more about this topic. As usual, I have my own example problems I've pre-recorded for you, so you'll need to watch those as well. So here's an application of calculating the moment of a force about a particular axis. Now, let's say that the mechanic here is using the wrench to turn a fastener of some type. They're applying force P as shown, and the moment you care about, or the torque you care about, is the moment about a vertical axis, because that's the axis the screw is going to turn through, right? So if a person's providing this force P and creating a moment MA, does all of that moment actually attempt to turn the socket, or is there a component of the moment that is not useful or that could even be detrimental, perhaps? Here's another application where we've got some shaped part. What this is used in, I don't know, but the part is constrained so that it can only rotate about the x-axis. So you can see how that works, but some force is applied at point B that tends to cause rotation about A. Now let's just say that for this bracket there's a certain amount of torque that's required, say from friction or something, such that the part starts to move about the x-axis. And the question becomes, how much force F do you have to apply to get this bracket to start turning? Now, hopefully your intuition is strong enough to see that not all of that force goes to try and cause a moment. Now, obviously, the vertical component of that force will cause a moment. Is there any other component of the force that will cause a moment about the x-axis? Well, that's a good question. You'll be able to answer that question because you'll be able to compute the moment of force F, which is just an arbitrary force, about the x-axis. Now, with scalar analysis, it can be a little bit different, but basically what you have to do is calculate the moment first, and you can always do that based on the shortest distance from the point where you want to calculate the moment to the force's line of action, and that will give you the moment of the force. So how would we perform this scalar analysis? Well, in this figure you see a tire iron being used to try and remove a lug nut from a wheel. The person is applying a force F directly up with their hand. And if you calculate the total moment of that force versus point 0, or about point 0, then you would have to take distance r, the cross product of that distance r, with force F, so r cross F. And when you do that, you would calculate all of the moment m naught, which is shown to not line up with the axis of the nut. You see, the axis of the nut is along the y-axis, but the total effective moment of this force is m naught, which is simply r cross F. Now, if we want to calculate the moment along the y-axis, then what we need to do is take a component of that resultant moment. But the easiest way to do that is to simply calculate the moment of the force that actually acts about my. In other words, take F multiplied by the distance from F, or well, I should say from O, to the line of action of F. So basically that distance, the text below refers to it as dx. That moment arm is the distance between F and really the rotation line of O along the x-axis alone. And that's the moment my that tends to act to actually remove the nut. The other component of the moment actually lies along the x-axis, and all it does, if you take your right hand and point your thumb in the direction of the x-axis, all it does is to try and round off the nut. So what it's trying to do is get that wrench to rotate upward and come off of the lug nut that way. Now it's not always easy to intuitively figure out which distance you need exactly, or to figure out that it's, the vector r times the cosine of theta. And so sometimes it's just easier to use vector analysis. In fact, I would say often it's easier to use vector analysis. So let's see how you would do that. So let's say we've got this general body here. It looks like a bag of water or something. I don't know what they've indicated by this, but we're interested in the AA axis, the vertical axis that runs through this body, and we've got some force F that's applied out at point A on the body, and a radial position from point O, the origin, out to point A. And what we'd really like to do is figure out what's the tendency of F to cause rotation about the A axis, the vertical axis. Well, we could calculate the moment of that force about at some point O that lies on the A axis by simply taking the cross product from O, using the position vector from O to A, crossed with the force F. So that's all of the moment m naught. That's not the component of the moment that lies along the A axis. Once we've got that, if we can write a unit vector along the A axis, then all we got to do is take the dot product of the unit vector with the total moment. In other words, take the component of the total moment that lies along the A axis. And remember the rule I told you about your thumb. Point your thumb along the A axis, and then your fingers indicate the direction of twist that a moment about that axis would cause. And so that's why the vector for the moment points straight up. That's a way of indicating the twist. And of course the slide shows sort of a blue curved arrow to indicate the effect that that black MA moment would cause on the body. So that's how you do it. And if you extend that just a little bit, if you include that with the full expansion of the cross product of R cross F, then you can calculate it all in one fell swoop. Now notice that MA comes out not as a vector but as a scalar, because we take the cross product of R cross F, which is itself a vector, but then we take the dot product of the unit vector along the axis of interest with the resultant total moment, and of course a dot product yields a scalar. So this method of calculating the moment about a particular axis is actually called the triple scalar product, because you end up with a scalar and you've got three vectors you're dealing with here. Now be careful, let's make sure you understand this. U naught represents a unit vector along the A axis. R is the position vector from any point on that axis to point A on the line of action of the force, and then F is the force vector itself.